I'm going to record example that we started in class, and this is problem 571 in Hibbler, the 15th edition. So first I'm going to go over what we talked about in class and go through all of the equations in essence and then start the solution. We weren't able to finish on Friday. However, since I had jury duty and no one was able to take over the class, I decided I'd go ahead and record. That way we don't use up that extra time period. Also, I think that it's might be better if you have a recording because you can always go back and look at it and maybe figure some things out based on what I'm saying so that you don't miss anything. So again, we're going to start. I'm going to explain a little bit about what we talked about on Friday. In this problem, it says we want to determine the tension in each cable and the components of the reaction at D needed to support the load. If we look at our setup here, we have our components at D that we're looking at here against the wall. And then we have the tension in cable AB and AC that we're also interested in. Step one, as I said in class, is to determine what the coordinates are for A, B, C, and D because we're going to need them when we work through our problem. Knowing the coordinates helps us determine the position vector, and we need the position vector to determine the unit vector. So if we look over at a free body diagram of that same drawing, then of course we have our member AD, and then we have the tension in cable AB, the tension in cable AC, and another force being pulled down into the right in the positive y direction, but the negative z direction at 400 newtons. We also have three reactions at D. That is because this is a three-dimensional equilibrium problem, but this is a three-dimensional problem. So we have dx, dy, and dz. And then we have all of the measurements set up in our free body diagram. So we know that to calculate a vector f, that we can find that by multiplying the magnitude of that f times the unit vector u. We also know that we can find the unit vector u by taking the position vector, and again, the position vector is the coordinates of the tip minus the coordinates of the tail, divided by the magnitude of the position vector. So I have the position vector r is equal to x tip minus x tail in the I direction, y tip minus y tail in the j direction, and z tip minus z tail in the k direction. Remember that the tip is where the arrow head is. So even though you may start at A and end at C, actually C is the tip and A is the tail. Be very careful about that because it will change your direction. Then to find the magnitude of the position vector, it's just the square root of the sum of the squares of each one of the components. Finally, we want to take the sum of the forces. Those are equal to 0, otherwise it's going to be moving, right? In this case, they have to balance each other out. We have the tension in AB, the tension in AC, plus the force of reactions or the vector at D, which is the reactions of dx, dy, dz, plus our F vector, which is the 400 newtons down and to the right. So notice this is the vector sum. So if we're going to add all of those components, all we have to do is get them into the Cartesian coordinate system. That would be the easiest. And then just add the I components, the j components, and the k components, and recognize that they have to all equal 0. Again, we need the vector of our force at D. That's just going to be based on how we drew our reactions. We have negative x, negative dx plus dy plus dz, all times their unit vector Cartesian system. Then we'll also take the sum of the moments about D. so that we can knock out dx, dy, and dz. They will no longer have a moment component because their line of action is through the point about which we are taking the moment. Therefore, we only have to consider the components of the tension at AB, the tension at AC, and our 400 newtons down and to the right. So in class, we had started first determining what our tension vector look like in AB and AC. We don't know the magnitudes. Of course, we're going to have some number of equations and unknowns. In this case, the vector or the tension vector in AB is equal to the magnitude of that vector times the unit vector, which is the position vector AB divided by the magnitude of AB. And what you have here is the result, which is negative magnitude of the tension AB times 6/7 I minus the tension AB times 3/7 J plus the tension AB times 2/7 K. We did the exact same calculation for the tension vector AC, and that is the magnitude of AC times the unit vector AC, which we can determine by taking the position vector AC and dividing by the magnitude of that position vector. Again, that gives us the vector of the tension AC is equal to negative tension AC times 6 divided by 6.3 I plus tension AC times 2 over 6.3 K. In this particular case, there's no J component because both of the components are on the same line. If we look over here and we look at your J component, which is Y, both C and A are along the same Y, or a plane that goes through the same point of Y, which is 0. Therefore, there is no J component, and that's what we're seeing here. We only have X and we only have K. So that's where we left off. We're going to go ahead and continue finding all of the components, and then we'll start taking the sum of the forces and the sum of the moments. Let's also go ahead and look at our F. Our 400 newtons is again down and to the right. So we have a 30-degree angle with the z-axis. And so we can also figure out the different components associated with our F. That would be 400, and then opposite would give us the opposite the 30 degrees is our J component. Adjacent to the 30 degrees would be our K component. So we have 400 opposite or sine 30 degrees associated with our J component, and that's positive because you can see it's down and to the right. So in the Y direction, this is a positive, but in the Z direction, it's a negative because it's moving down. So we have minus 400 cosine of 30 degrees K. So let's go ahead and take the sum of the forces, and we're going to do it by Cartesian coordinate. So if we look at our tension AB in the I, we have 6/7 or negative, let's separate this, negative 6/7 TAB. Then our F or our TAC in the I, we have negative 6 over 6.3. And we also have a dx component, and we have assumed our dx to be negative. With our F, there is no I component, so that's it for our I's. Then we have our j's. So again, our TAB is negative 3/7 TAB. There's no j component in the TAC, so that's 0. In our F, we have a j component of 400 sine 30 degrees. That is 20. No, I just calculated that, 200. And then our dy is positive, or we've assumed it to be positive. Lastly, in our k component, and I'm going to put that on a separate line just because it doesn't fit there. In our TAB, we have positive 2/7 TAB. Then our tension in AC is positive again, 2/6.3 TAC. For our D, we also have a Z that we're looking for, and we've assumed it to be positive, so plus DZ. And then our F, which is negative 400 cosine 30, and I calculated that to be negative 346.4. That is in our K component. All of this is equal to 0. Now, since this is in equilibrium, each component of our Cartesian coordinate must also equal to 0. So this must be equal to 0, otherwise it moves in the x direction. This must be equal to 0, or it moves in the y direction. And this must be equal to 0, or it moves in the z direction. So that means we can separate each one and set it equal to 0. Now, if on the left-hand side you, for some reason, have some ijk, then it would be set equal to whatever was on this side. But right here, we've already said that the sum of our vector forces is equal to 0. Therefore, the left-hand side is also equal to 0. So let's start. I'm just going to do this in a different color because there's a lot of red on my tablet right now. So let's start by setting each one of these equal to 0. So we have negative 6/7 TAB minus 6/6.3 TAC minus dx is equal to 0. Then we have on the other side negative 3/7 TAB plus 200 plus dy is equal to 0. And then we have 2/7 TAB plus 2/6.3 TAC plus dz minus 346 is equal to 0. So right now, looking at this, it looks like we have 1, 2, 3, 4, 5 unknowns and 3 equations. So at this point, we really can't solve for any one of these. We could solve maybe FAB or TAB in terms of dy, but that wouldn't really help us. So each one of these, it's really the d that's causing us some hardship. So we know that we can also apply the sum of the moments about our point. We've already talked about that on Friday and then previously when I introduced this. So the easiest way to do this is then to take the cross product. So let's say that we're doing, which we are, the moment about D. And I have the forces just as I've shown you. I don't have any free vector moments. I just have the forces that are causing a moment about D. Then the easiest way to do this is to take the line of action to A, and let me scroll up. I don't want to be moving this around too much because I don't want to make y'all dizzy. So what I'm going to do is take this like this, copy it, and then move it down here so that we have easy access to looking at it. That'll make it a little bit easier. So we're going to take the moment about D, right? As I mentioned, the easiest way to do this is actually to recognize that all of these meet at A. So TAB meets at A, right? I mean, it's in the name, A. TAC meets at A, again, A. And F is through A. So recognizing that right here is a point of confluence. I'm going to highlight it because that erased. For my TAB, TAC, and my F, then I can just take the perpendicular distance for all three of them from A to D. Now, remember that TAB and TAC have X, Y, and Z components, just like F had an X, Y, and Z components. So recall from when we started talking about the cross product, the easy way to do this, otherwise you're going to be doing a lot of geometry. The easiest way to do this is just to do the cross product times your vector, your resultant vector. In this case, and I already discussed this when we talked about the equations, in this case, because the moment is being taken around D, then the sum of those forces only includes your TAB, your TAC, and F. So this really makes it so much easier because I want you to check this out. Let's look at our DA. This makes it super simple. Your position vector, DA, right? So it's starting at D, ending at A, which means A is your tip. So if we take our I component, the tip of A, which is along X, the X component of A is 6. The X component of D, of course, it's 0. The Y component of A is 0. The Y component of D is 0. Similarly, if we look at our Z component, the Z component of A is 0, and the Z component of D is 0. So our position vector, which makes this super, super simple, is just 6i. So it makes it so much simpler because now, well, let me draw the matrix and then you'll see. So the sum of the moments, once again, the sum of the moments about D is equal to the following matrix. So we have our I component, our J component, and our K component. I'm leaving space because you know that we don't actually have numbers. We still have equations that we're going to plug in here. So our position vector is 6, 0, 0. We know that, no problem. If we look at our components over here, right, and we're taking the sum of the moments about D, we don't include the D component, but everything else will be included in our matrix. So that's going to be our I, this is going to be our J, and this, including that one, is going to be our K. So let's go ahead and plug that in. We have under I, negative 6/7 TA minus 6 over 6.3. That should be TAB. I don't want to get y'all confused. TAC. Looks like we don't have enough room, so let me move this over. For our J component, we have negative 3/7 TAB plus 200. And once again, looks like we won't have room for our K component, so let's move that over here. For our k component, we have 2/7 TAB plus 2/6.3 TAC minus 346.4. That is our k component. So first off, start here. Look, when we're doing I, which means we're not considering that line, we're not considering that, right? We're only going this minus this. Well, sorry, it went the wrong way. This minus this. Notice you have 0 times the k component, and again, j times 0, which means there's no I component in our moment. So we can just knock that straight off very easily. The other two will have components because when I look at j, right, so I don't consider that, I don't consider that, but look, I have 6 times this component, 0 times that component. So we will have, and of course, since that's j, that's negative. So let's go through and we'll say the sum of the moment about d is equal to negative, because this is a j component, 6 times 2/7 TAB plus 2/6.3 TAC minus 346.4. That's our j. Now, when we look at k, again, we don't consider that, we don't consider that, we just have 6. So the second part of that is also going to cancel out because we have 0. This one is positive, so this should be plus 6 times negative 3/7 TAB plus 200. And of course, this one is k. That should be equal to 0. Now again, I already mentioned this before. I'll mention it again. The sum of the moments must be equal to 0. The great thing about Cartesian vectors, Cartesian coordinates, is you can group all of those components together and just say, in this direction, they must be equal to 0. So j is not going to help out k, but the sum of the moments that are created by the components that are going in the j direction, right, or creating the moment in the j direction, must be equal to 0. Otherwise, you will have rotation in the j direction. So we can again set each one of these equal to 0. And I'm going to start with the k component because clearly I can see that I can solve for the tension in AB using the k component. So we have 6 times negative 3/7 TAB plus 200 equals 0. And so you can go ahead and solve through. I'm going to say 6 times 3 is negative 18/7 TAB plus 1200 equals 0. Therefore, my tension in AB is equal to 466.66, and onward. And as I told you before, we typically take it in 3 significant figures, so this would be 467 newtons. Now, since I have the TAB, I'm going to take that into my next section in the j direction because I have TAB. Then I'll only have TAC left. So we're going to go ahead and substitute that in 467 into this component. So we have negative 6 times 2/7 TAB plus 2/6.3 TAC minus 346, and of course that's 346.4 and so forth, equals 0. And therefore we have negative 12 over 7 times 467 minus 12 over 6.3 times our tension in AC plus 2076 equals 0. Then we can solve for TAC, and we get 673.8 newtons, or 674 newtons. Now we have our tension in AB, our tension in AC. We can substitute those back into these equations up here. So I'm going to go ahead and start with this equation and calculate dx. Let me just copy that down. So we have negative 6/7, this should be TAB, times 467 newtons minus 6 over 6.3 times 674 newtons minus dx. And that gives us dx is equal to, so that does give us, I recalculated to make sure, negative 1042 newtons. Which means, even though we assumed, like actually when I looked at the picture, we did assume dx in the positive direction, but then for some reason I wrote dx in the negative direction. So it is indeed positive direction. So you might write like 1.04 kilonewtons, and then that would be positive. It's in the positive direction. Next, let's go ahead and pull the others because we need to calculate our dy and dz. So let me copy this over and bring it down over here. So again, this is negative 3/7 TAB is equal to 467 plus 200 plus dy. Actually, that means that dy is equal to 0, right? Because this is actually 466.66667, so that cancels. That should be negative 200 plus 200, therefore dy equals 0. Interesting. Next, we have 2/7 times 467 plus 2 over 6.3 times 674. Oh my goodness. Plus dz minus 346. Here's another one. dz equals 0. Well, so my original supposition that it was going to move in a certain direction was completely incorrect, because the dy and dz is 0. But in this case, and one thing that I left off, which always remind, is that the tension in AB, while it's in the negative direction, it's in tension. So it's actually positive because it's in tension. Clearly, this is also positive in tension. So I believe I mentioned that. Your dx, dy, and dz are equal and opposite, but those are reactions, so they're considered external. So just be careful about that. If you want to put the direction, clearly this is going this direction and that's going this direction as well, but it is intention. So that's it for this example. I hope it was helpful, and don't skip too many of the parts because I do mention little things that assumptions and things like that.